last time I ended that we will be getting into cross product. We did dot product, now cross product. One of the most fundamental thing that one has to know about, or when we do cross products, is a matrix. Well, do we know what a matrix is?
Isn't it a set of isn't it a system of equations, basically, like a linear system of equations?
Linear system of equations, okay. What is the point?
I always thought of matrices as a sort of cross product. It's just
It is a cross product. That's exactly where we're going. But I want to put it in terms of, vector spaces. Geometry, because we were talking about vectors.
it's when you have a vector, it's always the orthogonal direction that is the resultant.
Okay. Let's see. You actually had the right answer. When the very first day of classes, I mentioned that we're going to do vectors in terms of geometry and space. But as a start session, I think of vectors in a different way, right? The colored vectors. In linear algebra, if you look at a matrix, let's say you have 2, 1, 1, 2. Good. If someone, you can invert this matrix. If you have another matrix, you can add. You could do a bunch of things. But if someone asked you, well, what is the meaning of that matrix? What does it do? What is the purpose? Well, if we have AX equals B, that would be a linear transformation. Yes. Set of linear equations. We did take pre-calculus, right? Should have done this, didn't?
I didn't take pre-calculus.
Cancer, come on. But do we know about matrices? Yes? Okay. So what it pretty much does is it takes this vector and transforms into that vector. So what we are trying to find is an appropriate matrix, A, simply transforms vector X to vector B. By all means, A is a linear transformation. That's something that you've got to keep in mind. Good. It's not a nonlinear transformation, linear transformation. Great. What is the simplest matrix that you can think of other than a zero matrix?
One.
Yeah, just ones.
Huh?
Just ones.
Other than, I knew this that was going to come, I should have been more specific. Other than a zero matrix, other than a matrix that is filled with the same number. What is the simplest that you can think of?
Could you just do like a 2-number matrix instead?
That's the simplest one. I'll give you a hint. It has something to do with the unit vectors.
Okay. 0, 1.
That's a vector. I want the matrix.
I don't know how to say it as a matrix.
We did it in class.
You did that?
Yes. Okay, what are the two
Matrix.
unit vectors?
0, 1, 1, 0.
0, 1, 1, 0. We know I vector from 0, j vector, 0, 1. And if you put them together and wrote it as a matrix, you would write that matrix as 1, 0, 0, 1. Good. That matrix has a name.
Unit
Very good, Chase. It is known as unit matrix in some instances, but it has a general name. Starts with the letter I, ends with the letter Y, and everyone here has got it.
Identity.
An identity. Good job. So it is an identity matrix. Some would write it as that. Some might write it as that, to be specific. I2 simply means it is an identity matrix in 2 dimensions. I3 would be an identity matrix in 3 dimensions. And I can extend this further. Why does it matter? Because if we are referring to vectors and matrix is a transformation, we need to know the basic one. The basic one is simply 1, 0, 0, 1 as a transformation. Consider the transformation I times x. So you have the identity matrix, you are multiplying by x. What would we get?
Can you rephrase that?
If you multiply I by x, what will we get? What is the answer?
Is it 2, 0, 0, 1?
Okay, any other answers?
2002.
Come again?
2002.
2002. Okay. Any other answers? When did you guys learn about matrices?
Never.
Static.
Never. In start.
Through homework.
I've been static.
Through homework and other classes.
I got 2-dimensional arrays and programming, but I don't think that rolls over, so.
I mean, 2-dimensional arrays and programming simply meant matrices anyways.
Yeah, well, we're now doing math, so.
Okay. Function correct. I can look at this function as a bunch of vectors. Each point, agreed. Every single point on that function can be represented by a bunch of vectors. Do we agree? Infinitely many. What is the definition of a function? Y equals f of x. Yes. What does a function do?
It combines a numerous amount of points into a specific direction.
It combines a numerous amount of points in a specific direction. In other words, well, let's take a simple case. Y equals xy. What does it do?
Makes a parabola.
Makes a what?
Parabola.
A parabola, okay. For each value of x, you end up getting a y value. And you start drawing tangent. That's not a parabola. I need to go back to algebra. So a parabola, yes. Okay. A function is a transformation. It takes values from X, maps it to Y with me. So you can think of a matrix as a giant transformation of sorts, but it has to be linear transformation. That said, identity means Chase mentioned it at the beginning. Go ahead, Chase, repeat what you said. When I asked, well, before I went to identity, I asked, well, what is the simplest matrix? I gave you a hint. It's got a bunch of unit vectors.
I said unit matrix.
A unit matrix. Unit means magnitude of 1. Yes. If you take a number, multiply it by 1, what do you get? The same number. You take a vector, multiply it by a matrix, your identity matrix, you will get the same vector. It is just an extension of one dimension. Good? You may say, well, why do I need this? Well, one dimension, easy, y equals f of x. But if you go to 2 dimensions, 3 dimensions, or look at points on a curve as vectors, things change. Put a note here because it is going to come back later. That said, if I multiply I by x, it's like multiplying a number by 1. We're just extending it to 2 dimensions. 1, 0, 0, 1. Multiplying by the vector x. The result has to be the same. Good? Yes.
I'm so used to in statics and physics of it just being like an absolute value bar. Why do you put parentheses between both two?
That's absolute value bar.
Yeah,
That is a determinant. Now, some would write a matrix this way.
Yeah.
You say you meant square brackets. right?
yeah.
Some would write a matrix that way, some would do it this way. Either would work. I personally like it that way.
Yeah.
But I started with this because we've been writing vectors that way. So I just extended it and put parentheses instead. Good. Do we remember matrix multiplication?
Never did it.
Never did it? Okay. I like to think of it this way. Well, what is the dot product of 2 vectors?
Just the multiply together.
You're multiplying what?
The components.
The components. Agreed. Dot product of the first row and the column, excuse me, and this vector will give you the first component. Dot product of this vector and that one will give you the second component. Good. In other words, what is the dot product here? How do we find it? 1 times 2. Yes. And then 0 times 1. What else do we do?
Same thing for the bottom two.
Well, when you find the dot product of 2 numbers or 2 vectors, do we get a vector or a single value?
You get a scalar. So we
A scalar. So what should we do?
you add those two.
Add those 2 together. Yes. Repeat the same. 0 times 2 plus 1 times 1. Good. The way I remember is when I first learned way back when. You might think I'm morbid and weird. I am. So running over a cliff, and job.
I was taught a different way.
Wait,
With
what?
matrices.
You don't like this way?
Not really, I'm just not used to it though.
So, run, jump, what is your way?
Well, usually we would put the first unit vector at the top and the second at the bottom. And then if you're looking for I, you cover the I and then you go to the J and the K.
Where?
To cover the J, you go to the I and the K.
You are referring it to, or you are talking about matrices in terms of I vector, J vector, and K vector.
Yes,
You're thinking about cross product. I haven't gotten there yet, right? I have not gotten into cross products. All I'm talking about is what a matrix is, what is its purpose, that's all. And how do you do matrix multiplication? We will get to I vector, J vector, K
put it on the
vector.
back burner. Okay.
So that is more of an application of this. But you've got to know what this means, right? I don't like to simply say, oh, multiply, get an answer, you're done. You've got to understand the meaning behind it. Dot product, running on a cliff and jump.
Where are we jumping? I see we go that way, where?
I mean, where would you jump? If you're on a cliff like this and jump,
You just fall.
you just
Or
fall.
you just stop short.
Okay, I'll just-
Now, what I mean is an easier way to remember on how to carry out, even if you forget that you have to find the dot product of this row vector and that vector. But there's an arrow that would help you, and I'm doing dot product of this vector, that vector goes there, that and that goes on.
Oh,
Yes, run, jump. Okay, 1 times 2 is 2. 0 times 1, 0. 2 plus 0, 2. And 1. Good. Take a vector, multiply it by the matrix I, which is the unit vector. You would end up getting to 1. If you think about it separately, all we did is took the unit vector, multiplied vector 2, 1. Yes. What will you get? So vector 2, 1, let's say is A. A is 2i vector plus j vector. Agreed. I just wrote it in a different way. That is a unit vector in the direction of which axis, x or y?
X.
X. Okay. When I multiply those two, in simple terms, you are multiplying an identity vector by another vector or a unit vector with another vector. Well, it'll only pick the x component because you are multiplying the unit vector corresponding to x. So that would be 2i vector. Yes? If you did 0, 1 and you multiply 2, 1, it is going to pick only the y component because the x component is 0. You will get j vector. Yes? And x component, y component, you have 2i vector, j vector corresponds to that. So another way of looking at matrix multiplication. But too tricky, this is easier. Okay, with me so far. Take a simple case. I don't want to do 2, 0, 0, 2. Too easy. Zero. Good. If you have to write this, you would write it as full J vector. That is to I vector. Agreed. I just broke the components over there. It's a different problem, but you get the idea. Okay. That is my transformation. Erase. If I took 0, 4, which is a vector, so I can write it this way. Good. Multiplying it by the transformation to 1, 1, 2. Let me so far. Vector 0, 4 multiplied by the transformation. Give it a try. Tell me what the result is. You know, we've got to do matrix multiplication. I did the simple case. Let's see what you get with that.
I understand it.
Joe asked a question. A good question. So could I multiply this by that? Cannot, because each value, resulting value, is a dot product. So you can't do the dot product of a vector with 2 components with a vector that has 3 components. By all means, they are in different spaces. This is in 2D, that is in 3D. But can't do. Okay. Dot product of that and that. 2 times 0 plus 1 times 4. 1 times 0 plus 2 times 4. Agreed. The result has to be a vector. It can't be a single number. Well, I have 4 and 8. Good. Okay. 4A. Is on a line. I'll give you a hint. What line? I already went over this part. If you have a function, every single point on that function is a bunch of vectors, you know, with the initial point at 0. That is a vector, and I'm going to tell you that vector is on a line.
The line y is equal to 2x.
Very good. It is on the line y equals 2x. That is that. 4A. 4, yes. A. Origin. Good. So it took these 2 vectors and created another vector. I'm sorry. It took this vector, created another vector, which is this one. So I took 0, 4, multiplied by the matrix A, I got that vector, 4A. It transformed this to that. Agreed? Okay. Vector 4A. I want you to take the matrix, multiply it with the x vector that I have over there. Did I call it A vector? No, but X vector, Y vector, how about that? So this is X vector, Y vector. What I just did was matrix A times Y vector. When I multiplied, I got a vector, I'll call it A vector. This one. Here. I just want you to connect the dots between matrices and vectors. Good? With me so far? He asked a good question. Why can I not do Y vector times A? Matrix multiplication is not commutative in the sense A times B is not equal to B times A. Often that's that. There is more to this. This is not a class in linear algebra. This is not matrix analysis. So keeping it simple, simply connecting matrices to vectors. That's all. A times X vector. A is 2, 1, 1, 2, X, 2, 0, 2 times 2 plus 1 times 0, 1 times 2 plus 2 times 0. Run, jump, dot product of this vector, that vector, dot product of this one and that one, you get 4 and 2. Yes. Okay, it's an easy case. If you looked at the results that we got, this is a simple case. Okay. There is a connection between 0, 4 and the results that we got, A vector. Or how about this? There is a connection between 1, 2 and the results that we got. What happened to the vector 1, 2?
It's in the same ratio.
Very good. It is in the same direction. 1, 2, it's right over here. It just got scaled by what value? 4. It's right there. Likewise, what is the other vector? 4, 2. X component is 4 right there somewhere. Y component 2, 4, 2. That's the vector. Yes, no, maybe. Great. Yes to no. That is some vector 1, 2, and when it was applied to 0, 4, we got 4, 8, but it is in the same direction of 1, 2. Yes. Going back to vectors, I can rewrite the second column as 1, 2. Agreed. A scalar multiple of the vector 1, 2 is simply distributed to each component. Agreed. So I'm going to multiply by a vector 0, 4, it is the same as saying 0, 1 times 4, scalar multiple. Multiplying 1, 2 to that. That is J vector. So what you pretty much did is multiplied the vector 1, 2 to 4J vector. See the connection? So take a column, multiplying it by 4, you simply took this and took 1, 1, 2 and multiplied that to 4J vector. Now, this is a nice case because the matrix is symmetric. Otherwise, you get a different result. I'm picking easy cases so you can understand. Well, what do I mean by symmetric? If you flip the rows, rows to columns, columns to rows, you still get the same matrix. Okay, this is not a class in linear algebra. Okay, so I've got this one, I've got that one, good. Now, geometry. In blue. I'm not a great artist, but that's okay. Yes. What do I have? Looks like a square, but it's not. Rectangle. Agreed. A rectangle.
Okay, yeah.
Right, based on length times width. Or length width. Okay. If you look at the shaded area that we formed, with the vectors 2, 0 and 0, 4, ended up getting this area. Yes, that area is nothing but hey. Good. Now, I want you to find the resultant of these two vectors.
Are you referring to y vector and x vector? Those two?
No,
Or
A and B.
A and B, okay.
So we transformed this to that and that to that. I got that region and I have its area. Keep that in your mind, that's the area. Now, those are the transformed vectors, transformed with that matrix. A times the vector here resulted in that. Matrix A multiplied by this vector gave me that. And I want to find the resultant of these two vectors. Why will it be?
On y equals x,
On y equals x. Why is that?
because a is, formula for a was, I believe, y equals 1/2 x, or sorry, 2x, and then the one for b is y equals 1/2 x. So the result between them would be right in the middle.
Did you follow what he said? So what we have in terms of a function, this is y equals 2x. That is y equals 1/2 x. We want to find something that's in the middle, which would be y equals x. But if I want to draw this vector, I'll arbitrarily draw one. start here, go that way, agreed? Not exact, approximate. Good. And then going to do that. And that. Good. I just completed to form. Now this one right here is the resultant. I don't want to complete that. But I completed with the vectors from this to that and that to that. There's, well, this, what I did had a name. If you did the homework, you'll know. Do we have to play the word game?
I feel like.
Start with the letter P.
Parallelogram.
Okay, very good.
It's so fun.
Parallelogram law, right? So you do the triangle, complete it, get the parallelogram. I want to find the area of that parallelogram. So what is that? Or how do we find it? Do we remember? Rectangle is a special case of a parallelogram, and if its area is base times height, it better work for the general case. Agreed? Base times height. Geometrically, you have a rectangle. You pull it, it becomes a parallelogram. That's it. So what is the length of the base? From here to there? Yes? Agree? What about the height? From here to there? Arbitrarily speaking. What do we get? Easy question. Height is this length is what we call height, right?
Yeah.
Length, or if you want to visualize it in a different way, length times width.
Wouldn't it
Okay.
be, I'm gonna try here, wouldn't it be 12?
12. How did you get 12?
Because 8 minus 2 is 6, and then you do 6 times 2 is the.
Where is the 2 coming from? You're close. This is the length of the base vector,
Oh, I
right?
see,
So it's
yeah,
4,
24.
24. Area there is 24. Good. Okay. I started with these 2 vectors. Yes. I applied the transformation. I got that vector and that vector. Completed the parallelogram with me so far. And then I wrote, or I shaded poorly, the area of a rectangle. The shaded area in orange is the area of that parallelogram. And how did I get that parallelogram? I simply stretched that rectangle. Would you agree that I transformed the rectangle? In what way? Well, that is the way. I used this matrix to stretch. So I stretched that rectangle. I ended up getting a different area naturally. Yes, stretching in different directions. So far, so good. So A applied to that is that. A applied to that is that. and completed, got two different areas. So a transformation, a linear transformation matrix applied to a vector will result in another vector. Why did I do all this stuff? Can I erase the middle part? Because we have the information that we needed here. And there. What do we know about determinant? I don't, again, I'm I am about conceptual understanding. I don't have, computations are important, but there is no meaning in computing something and not knowing what we're talking about. If I'm dead and gone, you should be able to explain to someone else, yes? So do we remember what a determinant is? No? Oh, yeah. Kansa said you took, I forgot his real name.
It's Caleb.
Caleb?
Yeah.
Okay. Go ahead.
What about a determinant?
You said you took matrices. What is the determinant of a matrix?
When did I say I took that?
Okay.
Said I did it on some homework, so that was about it.
So this is the line that Haley was mentioning earlier. That is the determinant of A. Some people will write it as det of A. Great. If you consider a 2x2 matrix, we'll keep that over there and I'll write the definition here. The determinant is simply A times D minus B times C. So it's AD minus BC. It's like a calendar, AD, BC. It has nothing to do with the calendar, but me so far, I want to find the determinant of the matrix 2, 1, 1, 2. Well, 2 times 2, A, D minus B, C minus 1 times 1. Good. Which is 3. Good. With me so far? Okay. Now comes the fun part. There is a connection between that area, and the number 3.
Oh, I see. Interesting.
I think that's an easy question. Carl?
8 times 3 is 24.
8 times 3 is 24. So if you have to explain in terms of areas, I said there is a connection between areas that rectangle, areas that parallelogram, and this number 3. And Carl said 8 times 3 is 24. So, geometrically, what does the determinant tell us?
Would it tell us the way it got stretched as well?
Very good. It simply tells us the magnitude of the stretch that was applied to that rectangle, given by the scalar 3. Good. So if you stretch a basic rectangle, provided you use that matrix A. You can't use a different matrix and conclude it's scaled by the same amount. But the matrix has to be A. So the area of a rectangle, area of the rectangle over here is simply the determinant multiplied by the area. Sorry, wrote it backwards. Don't want to confuse you. Area of the parallelogram is simply that multiplied by area of the rectangle. In that picture. So a linear transformation simply stretches two vectors in a different direction. But the two vectors that you start with will have an area that is enclosed, and you stretch it in different directions, you get a parallelogram. And if someone asks you, well, if you stretch, you are increasing the area. And if someone asks you, well, by what amount? For that transformation, the amount is 3. That is given by the determinant of the transformation A. Good so far? Okay. Now that we understand this in 2 dimensions, this could be applied to any dimension you want. Let's go somewhere with this. Determinants play a significant role when we try to find the cross product. Before we get to that, do you think that the determinant is always positive? In other words, no matter what transformation I pick, linear transformation in 2 dimensions, 3 dimensions, n dimensions, no matter which one I pick, do you believe that the determinant will always be positive?
Yes, because it's magnitude.
Oh, I think you misunderstood when I said magnitude. True, magnitude is the strength with which you are going to stretch. But
It can't be negative, and if you can flip it.
right,
Oh, so
can't
you're
be
referencing
negative.
direction.
Right, in
Okay.
reference to direction. So, Tracy used an interesting word, flip. What do you mean?
Well, if it's a negative, you can flip it over an axis depending on which part of it's negative. How you're multiplying across.
Okay.
Bad explaining, but depending on which numbers, because you can
Right.
have negatives.
So in
basis,
terms
yeah,
of this
sorry.
picture, what would it mean? This way?
Depends on what's negative. Like nothing's negative right now, so.
If your y turns negative, it would be that.
Okay, how about this? I've got x, y. I got a positive determinant. Stretched it this way, in that direction. What will happen if I had a negative determinant?
Smaller.
Smaller,
That rectangle.
I have 2 dimensions. I got a positive determinant, stretched it this way,
If it was negative, you stretch it that way.
stretched it this way for x, y. So you're simply changing the direction of the stretch, if it is positive or negative, relative to these 2 axes. Same rule applies in 3 dimensions also. So stretching this way, stretching that way is going to change the sign of the determinant. But regardless, that's the sign gives you the direction, the strength is still the magnitude. Okay. Clarified now. So determinants play a significant role in coming up with the cross product. And cross product is quite important because it has a lot to do with areas and volumes of shapes. I think the book goes over it. Cannot rest.